we're going to start. Somebody would ask if we are going to have these sessions in English. Partially, because it's a good idea if you practice, okay? Okay, so today, well, welcome to this Ship Dynamics class, okay? Today we are going to be doing three things. First, we're going to, two things. We're going to go over the syllabus of this class, so you know exactly what we are going to be doing during this semester. And then in the second part of the class, we are going to say a couple of words about reviewing our material from the prerequisite course, okay? So that's what we are going to be doing this afternoon. So I'm going to share. So this is the Ship Dynamics class. This is 2 hours per week. That's the theory that we call theory. And also we have 1 hour practice. By practice, we mean problems that will accompany the theory. So in total, we're going to have 3 hours per week, okay? And this is a fundamental course. That means that if you want to graduate from our university, from our program, you have to approve it. The prerequisite, it's mechanical vibrations. I'm using the new name of this course. It used to be ship vibrations. Well, right now it's different. It's called mechanical vibrations. And I put it like that because I wanted to have a course which can be considered as other programs. And if we call it vibrations, they might think that it is only for us. But I don't think that's correct. This is a quite general course. So if the name helps in some way, well, that's why I changed it, okay? And specifically, what we need from this course is oscillation of multi-degrees of freedom system, okay? And that's part of the first chapter, okay? And of course, if we remembered some of this oscillation of multi-degrees of freedom system, of course, we have to go through first oscillation of 1 degree of freedom system, so which is something that we're going to be reviewing this afternoon, okay? We're going to use 3 platforms. Zoom, we're using right now Zoom, and oh man, that's an error here. We have an error. We have classes Tuesdays and Thursday from 15 until 16:30. The other platform that we will be using is Teams, okay? And right now I'm recording this session. And in the afternoon, after the class, we will post these videos in Teams platform. Why Teams? Because our university has an agreement with Microsoft. So in general, we have a good space in Teams. So it's gonna be easy for us to post many things in Teams, okay? Also in Teams, please, Isaac, help me with that. We're going to include a file that we call a class log, okay? And in that class, we will be writing what are the topics that we will be covering in each session. Also, in that class, in some cases, we reach some agreements, okay? So I'm going to write in this class log file, I'm going to write all the agreements that we reach. So you know, for example, if you have to complete this or that for next classes or something like that, okay? Because in some cases, transmission gets lost or something like that, okay? So just to be sure that you remember what we have agreed on. And finally, the seed web, okay? The seed web, we're going to use it for homework and also for the evaluations, okay? When we have a homework, I'm going to post a homework next Thursday, I will post it in SeedWeb. And of course, you have to load your work in the same platform, okay? Evaluations, same thing. We're gonna do it using the SeedWeb. Evaluations are a big what? It's a big quotation mark for all of us, okay? And yeah, that's what we have available, and that's what we will be using for evaluations. So I will give you the evaluations on SeedWeb, and that's it. I'm not going to say much about that. This is the description that will be posted in the catalog. Please notice that this is an advanced course, okay? What do we mean by advanced? Well, that means that this is a 400 level course. So you are very close to graduating. So you are mature students, okay? And what we want to know is that, that you are able to calculate the response of a ship, there's an error here also, to irregular waves, okay? That means that in general, we are going to analyze the response of the ship when it navigates in real or quasi-real situations, okay? To do that, we're going to review some, it's probably chapter 2 and 3 from ship vibrations, which is the prerequisite of this. Then we're going to be using potential flow theory in order to calculate the added mass of simple bodies, okay? The hydrodynamic part of this course is a little bit more longer than the material that we covered in previous years, because in the new flow chart, the hydrodynamics class is not present anymore. So in order to try to avoid or to reduce the impact, because we don't have hydrodynamics class right now, we have put a couple of more hours in the chapter on hydrodynamics in this course, okay? And you would ask why? Well, the problem is that when the ship oscillates inside a fluid. So the ship moves and there is a pressure generated by this motion. And this pressure has to be calculated, integrated. That means that we calculate forces and moments. And those forces and moments will have to be included in the motion equations in order to calculate the response. Okay, so there is no way we can study ship dynamics if we do not include the hydrodynamic parts. Okay, so it's extremely important. Okay, so this is like the two chapters which gives us the tools that we need. And then we go, first, we study the problem of heave and pitch coupled. Heave is a vertical displacement and pitch is a rotation with respect to a transversal axis. That means that if you pitch, the ball goes up and down. Okay, that's what the pitch is. And also we're going to study in a different chapter, the uncoupled roll. Okay, so this is studied, but this is uncoupled. That means that we consider that the ship only rolls. It doesn't translate or rotate in any of the other axes, okay? And we do that first when we have regular waves, okay? Then in the next part, we study the response of a system, in general, a general system, to random excitation, okay? In this chapter, we will be defining, for example, the spectrum. What is a spectrum? Well, we will define it. And if we know the spectrum of the excitation, okay, we can calculate the spectrum of the response. That's something that we need. And finally, with the response of the, with the spectrum of the response, we can calculate some characteristics. And with that, we will be able to evaluate the response of a ship in irregular waves, which is the last part of the course. Okay, so this is the general description of our course. Okay, this is the references that we will be using. At the top, of course, our very well-known P&A, volume 3. This is the volume that we will be using. The volume 3 has 2 chapters. One is ship dynamics, and the other is ship responsive waves. That's what I mean. And the other is ship maneuverability. So we are going to be using the first chapter in that volume. And then we have some references, 7 references. Reference 1, you recognize our very well-known Thomson theory of vibration. Newman, the second reference, marine hydrodynamics. It's a classical book. It is in our library too. Third reference, it's Dean Dalrymple, Water Wave Mechanics. It's a nice, very nice book on water waves. Fourth, it's a reference that a couple of months ago, we prepared a work with engineer or Dr. Johnny Dominguez, okay? And I used this reference, Lloyd, to define a ship control system, an active ship control system. And this reference was extremely useful. So I think this is a good reference. Lewandowski, this is also a nice reference. It has a lot of information that we can use. Reference 6 is Imeno. Notice that it was published in 81. And the advantage of this is that it gives us some very nice equations in order to calculate the roll damping coefficients of ships. Okay, so in the chapter on ship roll, we will be mentioning this reference because this reference is quite useful if you want to estimate the roll characteristics. The roll damping characteristics of a ship. And finally, we're going to use MaxSurf, the program MaxSurf, to calculate in general the response of the ship to in very different situations. Okay, we can calculate it for a very simple situations. For example, in case of barges. But when we have to consider the general shape of a ship, that would be a very long process. And for that case, we simply go to this computer program. So at the beginning of each chapter, 3 and 4, we will be doing some calculations using or considering very simple forms, barges, okay, box barges. But when we try to analyze real ships, in that case, it would take too long to do the calculations. And we simply go directly to MaxSurf to analyze those cases, okay? So simple cases, we will do it by hand, let's call it like that. And more complex situations, more realistic forms, we will use MaxSurf. If you have any questions, please either you can raise your hand and I'll try to answer as soon as I can, okay? And we can go on. These are the course objectives. In the past, we have a little different, the first objective. Now, we put more emphasis on this. So we're going to use irrotational flow theory in order to analyze. This verb is very strong. So we will be able to integrate pressure and calculate added mass. Okay, we also going to review some main characteristics of gravitational waves, because we need this in order to calculate the action of the waves on the ship. Second objective is we want you to be able to calculate the response of a ship in the vertical plane, okay? We do that considering regular waves. And with vertical plane, we mean there's a combination of the vertical motion, that's what we call heave, and also the rotation with respect to a transversal axis, that's what we call pitch. Okay, those two motions, it's quite difficult to consider them uncoupled. That's why we have to analyze both in a coupled fashion. The third objective is you have to be able to analyze uncoupled roll motion. Okay, so consider that the ship receives waves from the side and it will respond with roll. The problem is that if we consider, for example, roll and heave, that will increase the complexity of the problem. So to analyze this problem, we consider the most simpler situation, which is uncoupled roll motion. So this is one single differential equation of motion, okay? And finally, we want you to consider or to calculate the response of a ship, but to irregular seas, okay? And to do that, we're going to use some statistical measures, okay? That's one, for example, the concept of RMS. Remember RMS from statistics? It's the remember mean squared, root mean squared. So we're going to use that, and we have to mention some other statistical concepts in order to handle this calculation. Okay, so these are the 4 objectives that we want you to be able to do at the end of the semester. We can go on. This is the content. So we have 6 chapters. Chapter 1 is the oscillation of systems with various degrees of freedom. We should say, I don't know why, but we should say here this is a review, because this is already been studied in the ship vibrations class. Okay, so that's material that comes from a previous class. Okay, application of potential flows. You see that this is 3 hours, this is 5 hours. So this basically almost double that. Okay. The third chapter, we're going to analyze in the vertical plane the motion of the ship. That means that we're going to be analyzing heave and pitch in a coupled fashion. Next chapter, uncoupled roll. So this is one single differential equation for roll. And the last 2 are very well related. And the first one, chapter 5, is an introduction to vibratory random response, okay? And there, basically what we want you to be able to see is how to calculate the spectrum of the response when you have the spectrum of the excitation. Okay, basically that's what we need you to calculate. And then in chapter 6, we simply apply what we did in chapter 5 to the ship. Okay, now remember that we have 2 lecture hours per week, okay? That means that chapter 1 will be covered in 1.5 weeks. Chapter 2 will be covered in 2.5 weeks. Okay, so more or less up here, we're going to have a quiz. Okay, this is going to be quiz 1. We will explain that in a few minutes. After chapter 3, we are going to have the partial exam. The partial exam will be covering mostly chapter 3. But of course, if you want to analyze the oscillation of a ship, you have to remember in general what the oscillation means. And also here, we will need some concepts from the previous chapter. So we're going to have quiz 2 here, which mostly covers the material of chapter 3, but you cannot forget what happened before. I mean, chapter 1 and 2. Okay? We will go on chapter 4 and 5, and here we're going to have our quiz 3. Okay? And finally, at the end of the semester, we're going to have our quiz 4, more or less. That's what it says here. We're going to have 4 evaluations. So first, 2, 3, 4. So we are not going to have an exam. This is a quiz 2. Instead of a partial exam, we are going to have a quiz 2. Now, the quiz 2 covers mostly chapter 3, but it is impossible to study this oscillation without the concept of the previous chapters. But in general, we will insist on chapter 3. Similar for this part, okay? The last quiz is not going to be an exam, it's going to be a quiz. Now, in this quiz, we're going to concentrate on the material of chapter 6, but forget it. In this quiz, we will need that you remember some concept basically from the whole course, okay? All of these quizzes are going to be 1.5 hours long, and probably they will have short questions, multiple choice questions, and probably the last part will be 1 or 2 problems to develop, okay? We will see how it goes, but that's my general plan, okay? So we will cover chapters 1, 2, 3 for the first part of the semester, and the rest for the second part of the semester. No exams. There will be 4 quizzes. There is some questions about the experimental part. Well, it is quite difficult to do experiments, okay? But what I have thought is if we find the correct material, we are going to give it to you. For example, we could give you, for example, some videos about experiment that other university has developed. For example, about waves, okay? And then I'm going to give you some data, okay? And then I'm going to ask you to prepare a report, okay? I know, we won't be able, in general, I'm not expecting to be able to go to the university and physically touch the experiments because there is a strong restriction on visiting our campus. And yeah, we have to understand the authorities, okay? They are worried that our facilities get infected, okay? And if the time comes, at the very end of the semester, if there is a chance, we will go to the campus and we will develop some experiment. But in general, I would expect not. So my plan is to give you hopefully 2, hopefully 3 videos give you some data and ask you to prepare a report. It is possible that at the end of the semester, there will be some permission to go to the labs. In that case, I would go with Isaac and Jose Maria, develop the experiment, video recorded for you, and we will share with you the information, and we will ask you to prepare the report. So those are two ways in which we could do the experimental side of this course, okay? That's the best that we can do. Now, for this work and also for the final project, I want you to prepare reports. And for that, you have to organize in groups, okay? I've thought that 3 is a good number. So I have 6 students registered. So we're going to have 2 groups, okay? I'm sorry. Okay, so you pick your groups, okay? Mr. Roa, are you there, Mr. Roa?
Hi, I'm here. I am listener.
Are you going to register in this class?
No, I am listener.
Okay, so you're just visiting?
Yep.
Okay, welcome.
Thank you.
I have 6 persons, so you have to organize yourselves and tell me your groups, okay? So 3 and 3. That's that. That's the legal side of this class. This is the way we are going to evaluate this class. In the first part of the semester, we're going to have, as we said before, we are going to have 2 quizzes. So it says an exam, but it's really a quiz, okay? So for the first part, we're going to have an exam at the 8th week and a quiz at the 4th week. So the quiz at the 4th and the quiz at the 8th, each one will value 35% of the grade. And the rest will be homework and laboratory reports. So you add 200%. For the second part, the big difference is this, and that corresponds to a project. Okay, so each group will have to prepare a project, and when the time comes, probably after the first exam, that means in 8 weeks, I will ask you to let me know what ship are you going to analyze for the project. So you have to start collecting information on the ship. So when probably in the 4th week after the exam, you will have to start doing, for example, the hydrostatic part of the calculations. So when we reach to the point, you will have all the information, hydrostatics, ready for the calculations in the dynamic side, okay? So this 20% that we're mentioning here will take some weight out of this, and this is the way we are going to evaluate. Again, for the second part, we're going to have 2 quizzes. The first quiz will be in the 12th week, and this other quiz will be at the end of the semester, like the final exam, and each one will value 30%. We'll have some assignment, 20, and the project will value 20. The project will have to be presented orally in a public presentation also. So you have to organize yourself because physically you are not in the same place. So let's see what happens, okay? But this is the way I'm going to evaluate this course. For the third evaluation, for the third Remember, this is typical of my classes. The university forces me to give you a third evaluation, but that's, for me, that's not correct, because that gives you the feeling that no matter what you do when you get engineer, everything will give you a second chance, and that's not true. For example, here I'm showing you two cases that probably you recognize because those were publicized in our news. So those are accidents that happen. I'm not saying that these accidents occur because of naval engineers, no, but it could be. And we have to worry about these cases, and we have to avoid these cases. How can we do it? Well, if we have one first evaluation, one second evaluation, and each one values 100 points, you need 120 to pass this class. You have to take advantage of these two opportunities. Do not think that we're going to have a second chance, okay? Yes, I'm going to give it to you because the university forces me, but it is very difficult, okay? So as a very practical way of thinking, consider that the third evaluation does not exist, okay? So when you become an engineer and somebody asks you to do a stability analysis, okay? Do it well the first time. Don't expect to have a problem to correct it, okay? Put your best effort the first time, and that's it. Okay, that's the message behind this regulation. And I'm not going to discuss it. This is what it is. Okay, there was some problems in one of the courses. Somebody told me that somebody got in one of these Zoom sessions and start projecting and doing things and noise and things like that. So that's why at the beginning of the sessions, you have to get into the waiting room, and I'm going to grant you permission to enter. Okay, so please, we're going to start each session at 3:10. So try to be about 3 p.m. and I will let you in. We're going to start sharp 3:10. As I said before, all of these sessions will be recorded, and later on, I will post it in the Teams platform. Student assistance will not be controlled, but in general, I would like to know, for example, if you start failing to come to class, I'm not going to call your attention, but in general, I'm going to try to get in contact with you and ask if there is any problem or if I can be of any help. Okay, in that sense, I'm gonna see who is coming and who is not. But it's not because I'm controlling the systems, okay? You may leave the class at any time you want or you need, please leave a message so saying that you are leaving, okay? For that, we can use the chat. Please, your phones off. We have very funny situations when you can listen to what's happening in your surroundings, okay? So we don't want interruptions, as my phone here rang, and please, phones off. What happens if you want to ask something? Well, there are two chances, okay? From time to time, I'm going to stop and ask if there is any question, okay? And then you can turn off on your microphone and ask, or either you can raise your hand, and when the time comes, I'll let you participate and ask your question. In this case, this is, well, it's always a good idea, okay? When you start asking a question, okay, why don't you start by saying your name, because in some cases, it is possible the audio doesn't help and we cannot recognize who is asking the question. Also, when you ask the question, it could be a good idea if you turn on your camera. So, because sometimes I feel like I was talking to the walls. And so it's a good idea for me, not for you, for me to see who is asking the question, okay? Sometimes you forget, don't worry, but if you can, do it. Turn on your camera also. The last regulation, okay, as I said before, assignments will be posted in the SIT web. You have to complete it, scan it, and load it in the SIT web also, but only in PDF format, okay? As we said before, homework is obligatory. You don't have the choice. You have to do it. You want to pass this class, you have to complete all homework. Daniel Miranda, you have any question, please?
Yes, I have a question. Well,
Sure.
two questions.
Sure.
Is this an English class or it will be in Spanish? Because
in general, I'm going to try to force you to use English, okay? In general. From time, for example, it is possible in the hydrodynamical part, since it's quite complex, probably I'm going to go in Spanish. But in general, in the class notes that I'm going to write and I'm going to project, all the things that I'm going to write here, probably they will be in English too. And of course, the homeworks and all that I'm going to give you and all the evaluations, those will be in English. Okay. Any other question, Miranda?
No, it's clear. So
okay, no.
homework, class questions have to be in English.
Yeah, it is possible, yes. Okay, if I see that it is quite difficult, as I said before, for example, chapter 2. Chapter 2 is quite mathematically complex, okay? And in that case, I will go in Spanish. But in general, I would like you to, for example, the final project, okay? Final project is going to be in English. Okay, so it shouldn't be any problem for you because you are in an advanced level course in naval engineering. So probably you have participated several times in the technical sessions. So you have the experience of doing this presentation. So it shouldn't be any problem for you. Okay, but yeah, we have to go the next step. Okay?
I have another question.
Sure, go on.
What about the journal technical sessions?
That's a very good question. We are going to try to have the technical session, definitely. And if, in that case, probably I will ask you to participate. I don't know if you are participating or taking the ship design course. Are you taking that class? Is there anybody who is taking ship design 1 right now?
Yes.
Yeah. But those of you who are taking ship design 1, you will probably participate with your projects. Of course, that one, if you participate once in the technical session, that's enough. But if not, yes, I would like you to participate in this with the project in the sessions, in the technical sessions. Yes. And of course, those are in English. Any other questions? No. Okay. The final part. Please, I need a proof that we have discussed these things in English in the class. So I will ask you to print this syllabus and class regulations, this document that I sent you. At the end, you will see, you will read this phrase. okay? And I'm giving you this space for your signature, okay? If your signature is very large, you can, there is a space above this line, okay? Here in the document, there's a space here. You can use this space to do your signature. You have to hand write your signature, okay? And then you scan it and send it to me, okay? If the time comes, you can tell me, oh, I didn't know. No, I have your signature, meaning that you read and I explained to you these regulations and you agree, okay? So forget about that. And for that, I need a proof, and this is the proof that I need. So please print, sign, scan, and send it to me, okay? Finally, office hours, okay? I will be available, especially on this time, Mondays from 4 to 6. Also, this is more difficult because remember on Thursday, we have also classes. So I'll try to be available at that time, okay? Thursday from 1 to 2. It's going to be difficult because then I have classes with you at 3, but I'll try to be available. And that means that I will have the system, the Zoom system, open. So you can enter the waiting room. And when I see that somebody's in the waiting room, I'll let you in and we can talk and you can ask any questions, okay? Since we are in a very new environment, I have asked Jose Maria and Isaac, they're here, and they will be available in these times, on these hours. The same hours as me, but also on Thursdays, they will be from 1 to 4. Oh, you cannot be in 1 to 4 because you are going to be here too. So they're going to be available from 1 to 3. Okay? These are the email addresses. And of course, we're going to have an assistant for the grading. But we are trying to select somebody. We will let you know who that person is, and also its schedule. Okay, so if you have problems with the evaluation, with the grades of a homework, don't talk to me. First, talk to the person who graded the homework. And if you don't reach any agreement, yes, then come to me. But first, you talk to the grader, to the course assistant. Okay, so this is chapter 1. Well, this is the ship dynamics class. Okay, and before we go on with our material, let's say a couple of words about ship dynamics, okay? In general, dynamics means that this area studies the motion. You have forces and moments on the bodies, and the bodies change its position on time. That's what dynamics in general means, okay? So when you say ship dynamics in English, you mean 3 things, okay? 3 areas, okay? One is what we call vibrations. The other is response in waves. And the other is controllability or maneuverability. The 3 are areas of ship dynamics, okay? In the case of ship vibrations, that means that something deformed. So, for example, we studied the deformation, the vibration of the hull, okay? So we have, for example, the hull vibrates. That means that the hull deforms. For example, we have local vibration. For example, it's typical, the ship propulsion system. Okay, in this case, for example, it can vibrate torsionally. Okay, in all of these cases, the system deforms. That's vibrations. The other area is responsive waves. That's what we are going to be studying in this semester. And in this case, the system, the ship, is considered that doesn't deform. Just a second. That means that it's just a does not deform. Okay? And in this case, we have 6 degrees of freedom. Okay? And the other area is maneuverability. Okay? These two, they are really oscillations. So the system moves around a certain equilibrium position. In this case, you don't have oscillations, but you have a behavior that depends on time. Okay? And here, for example, you study problems like stability of direction and things like that. Okay? So, in general, this is what we mean in English with ship dynamics. We are going to study specifically this. Okay? So, we are going to consider that the ship doesn't deform. So, it's going to be considered as a rigid body. In that case, we should go on and consider 6 degrees of freedom. That's a very complex problem. So what we're going to be doing, chapter 3 and 4, is a group of motions. In case of chapter 3, we will be analyzing the heave and pitch coupled problems. In chapter 4, we're going to be analyzing the roll response. Okay? So this is where we are going to be working during this semester. Let's go on. In chapter 1, in this semester, we're going to study the oscillation of systems with several degrees of freedom. Okay? As I said before, I think here we need a word, and the word review. I don't know why, but I forgot to include it, but anyway. Because this chapter is basically chapters 2 and 3 from ship vibrations. So I'm not going to go in detail. If you don't remember, get your class notes and review from there. So all I'm going to do is just pinpoint certain main concepts, and that's all. And of course, we're going to solve some problems, and at the homeworks, you'll have the opportunity to review. Okay? That's the way we are going to be working this, this chapter. Okay, so subchapter 1.1 is something like this, but instead of several, we're going to say a couple of words about the oscillation of systems with 1 degree of freedom. Okay? So it's an oscillation of systems with 1 degree of freedom. Okay, now, when we want to analyze the oscillation, the way we summarize the effects is with the use of what we call the dashboard. Okay, this is our dashboard, and we have an excitation here. Now, this is the summary. Of course, in the case of this class, we are not going to have something like that. But in general, we're going to have all of these effects. We're going to have a restoring effect. Okay? That means that if this moves, this effect tries to put you back in the equilibrium situation. This is the damping effect. This means that when you move with a certain velocity, this device will extract energy and put it away. Okay, so this helps us to limit the amplitude of the response. So that's good for us. And this is the mass. So this opposes to any change in velocity. That's what we call the inertia effect. Okay, inertia means that opposes to changes in velocity, opposes acceleration. That's what it means. And finally, this is an external action. Okay, something which is interesting is that the restoring action will be proportional to the displacement. The damping will be proportional to the velocity. And the inertia will be proportional to the acceleration. So you see that these three terms depend on the displacement. That's the function that we are trying to analyze, because this is a system that needs only one single function. And this is independent of that. So in here, this is independent of W. Okay? So these are the effects that we'll be including in our analysis. And the dynamics is summarized applying the Newton's law of motion. When we apply the Newton's law of motion, including all of these four effects, at the end, we will have an equation, remember, like this. Mass times acceleration, that's the inertia effect, plus constant times the velocity, that's the damping effect. Restoring, this is the restoring effect, like in a spring. And on the right-hand side, with no influence of W, we are going to have an excitation. Okay, in general, we're going to have this shape. Okay, so this is the system with all the effects that we are going to be considering in this class. And when we apply the second law of motion, this is the differential equation that we are going to be trying to solve. If we find W, that means that we are able to calculate, to analyze the motion of this, this system and of this, this block. Of course, for us, this block will be the ship. Now, in general, we will develop some analysis, okay? First, the free oscillation. And in the free oscillation, remember, there is no excitation, and usually we take no damping. This is identically zero because by definition, there is no excitation in the case of free oscillation. And in this case, we consider that if the result doesn't change much, if we neglect that, but we can analyze a much simpler problem, we do that. That's why we said, okay, let's take that equal to zero. And the result is the natural frequency. Sometimes we call it omega 0. And by definition, remember, that's equal to square root of k over m. So that's the free oscillation. And remember that if we neglect that, we have an homogeneous problem, okay? And the solution of that, or part of the solution of that, gives us this value for the natural frequency, okay? And the other problem that we are going to be working is the forced oscillation. Okay, in this case, we have to consider F, we have to consider C. And the main thing about the forced oscillation is that we're going to have an amplitude of the response and if we repeat here, the excitation has this form, an amplitude Fe omega t plus beta. The response will have the similar shape, but there will be a phase shift. We call it theta. Okay? And of course, this is extremely important for us, the amplitude, because this is something that we want to determine. If we have a very large value of W, that means that our ship will move a lot. Passengers probably will get sick. They may start vomiting, and we don't want that, okay? So that's what we want at the end of the semester, okay? Be able to predict if the response of the system reaches a value such that it causes problems to the passengers, or it causes problem to the crew, such that they will not be able to perform their duties. Okay? Now, what else? In the case of the forced response, remember, we draw, or we were able to calculate the amplitude W, this W, and here in the abscissa, we present the ratio between the excitation frequency and the natural frequency, okay? And when we are with a value of about 1, that means that these two are the same, the response of the system will increase. And this region, where we have this effect of magnification, this is what we call the resonance region. So, if we have an excitation frequency which is close to the natural frequency, in general, the amplitude will be increasing. That means that we are in trouble. So we have to do something in order to separate these two such that we are away from this resonance region and the response will decrease. Okay? Also, we see that there is a phase shift, theta. Okay? And in general, we say that the response is behind the excitation. That means that in general, theta is going to be negative. So the excitation does something and the system respond with a certain a little bit late. So the response is behind the excitation. Okay, so we represent that, remember, with the same ratio in the abscissa. And here, instead of plotting theta, we plot the negative of theta. So we will get a positive value, okay? And we usually have one value of 180, this is degrees, this is 90. And when we have the resonance, we remember that we are going to go like this. Okay? You will remember the expressions to evaluate those. Okay? Okay, let's remember that. We remember that W is equal to F over K. This is F. K is the constant of the spring. And we divide it by the square root of 1 minus omega over omega 0 squared. All of this is squared, plus 2 z omega over omega 0 squared. The phase shift is equal to the inverse of minus 2 z over omega 0 divided by 1 minus omega over omega 0 squared. Please remember, this expression, it's a good idea to put them in your memory, okay? We have this negative sign. That means that the response of the system is always behind. That's why here we plotted the negative of the phase shift. That means that we recognize that the excitation does something on the system, but the system takes some time to respond, okay? It's like if you are standing in your car in a traffic light, okay? You are in red. It turns to green. That's the excitation. So you see green, that signal goes to your system, to your brain, and finally reacts and change the shift to first, and you go on. So from the time you see the green light until your car start going on, there is some time lag. That means that you are behind the excitation. That's a classical example of this. Here we have this little snaky symbol. That's by definition, remember, that's the C divided by twice m omega 0. The C here, the C is the constant of the damping effect. Okay, so if you have a large C, you have zeta here, the W will be reduced. Okay, and when we plot this, we remember that we consider one single value of zeta. If we change that, for example, we reduce Z, then this thing will increase. And in this case, this will be closer to that. So in this direction, C increases. In this direction, C increases. So more damping, less response. Again, more damping, less response. Okay, so before we close up, this is something that we should have in mind is that some facts. If we have an excitation with the frequency omega, that it's like a mark that will be shown in the response. Excitation frequency, and that is shown in the response. The response will have the same frequency as the excitation. here, if we have large F, that's the amplitude of the excitation. Large F means large W. That's the amplitude of the response. You have larger waves, larger response. And finally, another thing which is very important is the fact that there is a minus sign here. So when you have this difference close to 0, this is the denominator. That means that you're going to have an increase in W. And that's what we have here. When you have this close to 1, this difference gets close to 0, and the quotient will produce a larger value, and that's what we mean by the resonance region. Those are, I think, the most important concepts of this 1.1 subchapter. Okay, if there is no more questions, then I'll close this session and we will see you next, when?
Thursday.
Thursday.